let's start. All right, so far we've been doing triple integrals and volumes. Okay, so in rectangular coordinates or in XYZ coordinate system, the triple integral of f of XYZ dV over some solid S in R3. If this was the density at each point of the solid, it could be a sphere or cone or cylinder, whatever it is. Okay. That will give you the total mass of the solid. I think most of our focus was on finding the volume. Okay, so in particular, the triple integral of 1 dV over the solid S, and so far we only talked about rectangular coordinates or Cartesian coordinates. That will give you the volume of the solid. And we talked about how dV would look like. Okay, there will be some height and then the surface area component. So this is usually some combination of dz, dx, and dy. And assuming that we follow a XYZ system like this, the dz usually stands for the height, and then the rest of it stands for the area of the base. Okay. So it's still what you learned in your middle school as the volume of a solid, except that the shape is getting a little bit more complicated here. That's why we need calculus. Okay, so that's where we stopped. But I think towards the second part of worksheet number 9 had a lot of problems which we probably did not want to do using X, Y, and Z. Okay, we saw that using a more circular kind of a domain or region would be more appropriate there. And that is what we're going to focus on today. So today we are going to do both sections 3.6 and 3.8. Okay. You don't have to be scared because there are 2 sections, but it covers the same concept. It's just that one of them is doing just volume, the other one is doing mass. Okay, but you're still doing triple integrals and cylindrical and spherical coordinates. Which are kind of both based off the polar coordinates that you saw in section 3.3. We are just expanding that into R3, okay, and also mass and volume. So that is the main content of what we're going to do today, and we'll be doing worksheet number 10. We will try to do most of the integrals completely, but if we run out of time, we'll be just setting it up and asking you to just finish it off yourself. Okay, so let's see how it goes time-wise. I'll try to finish both these sections today itself. But before I start that, now that I think most of your regular students are here, let me remind you of test number 2 on Thursday. So understanding today's worksheet is critical, okay, just to get used to these 2 coordinate systems. And there will be one more worksheet that will be tomorrow's, which is based on surface areas, which is actually not bad. It kind of looks scary if you look at the way things are done, but once you get used to it, it's pretty easy. So today's lecture, make sure that you understand all the minor details. That is where usually the difference between success or failure in chapter 3 would lie. All right, so first let's talk about cylindrical coordinates. I also posted a practice test for test number 2 and also the problems from the old final exams. While you're doing your homework today, please try to go and dig out those problems and see if you're comfortable doing those things. Yeah. Let me remind you of the polar coordinates in 3.3, because we are just going to expand it by a 3rd dimension. Okay, so cylindrical coordinates is just a very small extension of polar coordinates in section 3.3, which had this circular region with radius r and this angle theta, which is counterclockwise from the positive x-axis, and you had x equal to r cosine theta, y equal to r sine theta, and x square plus y square is r square, which I think was a very important part of your quiz last week, and also dA, which is a small area element here, is r dr d theta. So all of you know that at this point, and when we were doing some of those worksheet 8 questions, some of you probably would have thought, why don't we just use that? But we didn't officially create those, and that's why. So that's what you know from 3.3. So when you say cylindrical coordinates, a cylinder for our purposes is usually oriented along the z-axis vertically like this. It's called a right circular cylinder. That is the official name, though we just say cylinder. It's a right circular cylinder, which means it stands upright and with its height along the positive z-axis, and also it's circular in cross section. So yes, elliptical, you have to then adjust things. So the word cylinder is officially a right circular cylinder. And you're probably, it's easy to imagine this. A cylinder is nothing but a set of circular discs which are kind of stacked on top of each other along the positive axis. So this is a set of circular discs stacked up along the z-axis. If you just have one of them, there is not a lot of height, but if you stack up a lot of, you can just take your quarters and just stack up 100 of them, that makes it a solid cylinder. All right, so we can define the cylindrical coordinates as follows. So mostly it is just copy and paste. That's a good thing about cylindrical coordinates. Just borrow things from polar coordinates. You're still going to have x equal to r cosine theta, and that's because your cross section on the xy plane is a circular disk. If you look from the top, what you see is still this shape with the radius r and an angle theta. So x equal to r cosine theta, y equal to r sine theta, x square plus y square equal to r square, and tan theta is y over x, where r is always positive. Let me just keep reminding you of that. No matter which part of the circle or the circular region you look at, the radius is always positive, and theta goes from 0 to 2 pi, unless you cut it somewhere in between or take only parts of the circle. The angle goes from 0 to 2 pi. So all those things are here. The only extra thing you have is the third variable z, which is just z. So there is nothing new there. So the rectangular coordinates are x, y, z, and the corresponding polar coordinates in 3D, which we call as cylindrical coordinates, is just r theta z. So z remains z, and it just goes along the z-axis from bottom to top. There is no restriction on the z variable as such. So it would go from negative infinity to positive infinity. So that is one place where you could plug in any number and it's okay. Because you're just defining the height of the solid. So just no matter where you place it, whether you start from the origin or if you place it a little bit down, the height is remaining the same. All right, and then what else do we need? We need the corresponding term for the volume. So the volume dV is going to be dz, which is height, times the base area, which is dA, and that's going to be dz times r dr d theta, which again I'm borrowing from the polar coordinates. So not much has changed here. So the cylindrical coordinates is just a very easy extension of polar coordinates into 3D with the height factored in and creating a solid. All right, so we want to make sure that this works. Okay, so let's find the it's always nice to check something that we know, right? So if you take a cylinder of radius r and height h, what is the volume from your middle school? Pi r square h. So let's see if that is what you get here. Find the volume of a cylinder. Okay, once again, that is a right circular cylinder of radius r, radius capital R. Let's not mix up letters. And height h, capital H. And there is nothing wrong, or you're not losing any generality if you keep that cylinder on the xy plane, or if you push it down a little bit, the total height is still the same. Okay, so how you position the cylinder is not of any concern to us. Like this, and you could just place it like this, as though it is just sitting on the floor. Okay, so this height is h, and this radius is r. That should be the same here as well. And this is nothing new. All of you know the volume is pi r square h, but we are just trying to verify it using cylindrical coordinates. Again, don't forget the volume is just the triple integral of 1 dV. And the solid is the cylinder. All right, so that's going to be 1 dV is dz, which is the height, and the r dr d theta for the base area. And we are taking the entire cylinder. Okay, so there is nothing cut out from here. So the z goes from 0 to h, that is the height. R goes from 0 to capital R, theta goes from 0 to 2 pi. And suddenly what would have been a pretty complicated integral to deal with in x, y, z becomes just a product of 3 calculus 1 integrals. As usual, since the integrands are all kind of independent of each other, we could separate them out. Okay, so 0 to 2 pi d theta, 0 to capital R, r dr. Okay, don't forget the little r in there, and then the height, which is 0 to h, dz. Okay, so if you just collect all the components, you see the answer. That's 2 pi times r square over 2 times h. So that mystery is solved as to why the volume of a cylinder is pi r square h. Certainly math gets a lot easier. The more complicated things you bring in, it makes your life easy. Okay, so we can use this as a reliable thing. Okay, it's not going to fail anywhere because just verified something we've been believing all our life. Okay. So now let's go into the worksheet and start doing the problems there. This is worksheet number 10. Okay. This was not in the worksheet. I just wrote that as a sample. So if we could take worksheet number 10 and look at the first problem and see if there is a good candidate for cylindrical coordinates, and then start doing things. You want me to project it here? Okay. Draw a picture which might be helpful in some cases. Yeah. pay attention to all the words there. There's the word by there. Okay, so it says below by the cone and above by the paraboloid. So it's not below the cone and above the paraboloid. So the solid should look like this: paraboloid and a cone. There's some kind of an ice cream cone kind of shape, but it's not spherical up here. And it says half cone. I'll tell you why. Okay. And some students make it a big deal. So let me just clear out what exactly that half cone means. Remember when we drew pictures in the first week of classes? Okay. This was what we referred to as the complete or the double cone, z square equal to x square plus y square. Okay, there are two parts to it actually. So the upper cone and the lower cone. Okay. So when it says the half cone, we're just talking about this part here. The positive part of this cone. Okay. And sometimes some textbooks and some people who write it write as half cone. That's a full cone, half cone. Okay. So you don't have to further slice the cone into another half. Okay, that's what I'm trying to say here. My first question is, do you think cylindrical coordinates is a good option here? Looking at these terms, remember that when you did polar coordinates, our hint was to look for terms like this: x square plus y square. Do you see similar terms in these two surfaces?
As long as you look down from the positive axis down, the cross sections are all circles.
Okay, so that's a geometric way, right? So I'm just asking you, but what you said is right. Do you see this term in both these surfaces algebraically, visually? You do, hopefully, right? This one might take some, maybe a couple of seconds to see it, but it's there. It's 6 minus x squared plus y squared. Just to make sure that it's x squared plus y squared there. Okay? If this was 6 plus x squared minus y squared, it won't work. That's a bad idea, right? Either both have to be positive or both have to be negative for this to work. Okay? Because the other one is a saddle, and that is not really circular. All right, let me get rid of this picture here. So let's hope that cylindrical coordinates is good, because we have an x square plus y square here and in this surface as well. Okay. So use cylindrical coordinates. Remember that the z should define the height of the solid. Okay. So this is your, no matter where you stand, the z is defining the height. So what are the z limits here in terms of polar coordinates? Remember that when you go to cylindrical coordinates, everything should be in terms of r, theta, and z. So no more x and y. Z could hang around, but here, what are the limits for z? Yeah.
From square root of x squared plus y squared.
Okay. So.
Oh, you can write it
Mhm.
to square root of r squared. Or just r.
Okay. So this is this r. Okay. Let me just. This is the square root of x squared plus y squared, which is the square root of r squared. R is positive. Okay. So this is just r, not the absolute value of r. Okay. So the lower limit now looks incredibly easy because of the cylindrical coordinates conversion. Okay. So the lower limit is the cone, which is z equal to r. What about the upper limit? 6 minus what? R square. Okay. Please don't make the mistake of writing it as r. It's r square. Okay. So that defines the height. Okay. So you're standing on this conical thing and looking at the parabolic roof. Okay. So that will be the lower limit for z. That's upper limit for z. Now, what I said earlier was that when they intersect, you see a circular cross section here, a circular disk. Does that algebraically make sense? If you set those equal, intersection would be That's the shadow or the projection of what you see on the XY plane. So on the XY plane, which means when those two kind of get pressed on top of each other, so you have 6 minus x square minus y square equal to the square root of x square plus y square. Once again, take advantage of cylindrical coordinates. You know that this is 6 minus r square equal to r. That's why it is so much better to do this in cylindrical coordinates than in xy, because there you got all these things kind of lying around, and annoying is now you get just one letter r. This is a quadratic equation. You have to just solve it. There's nothing wrong about it. So it's r square plus r minus 6 equal to 0. I bring all the terms and keep r square positive. I hope all of you know how to solve this. You could factor this actually. This is r plus 3 times r minus 2. So we are trying to find the radius of that circle forming that cross section. So we get two values, r equal to negative 3 and r equal to positive 2. The question is, are my limits going from negative 3 to 2 or 0 to 2? What did I say about the radius? It should be positive, right? So what will be the limits for r in this case? 0 to 2. In other words, you discard the negative answer because radius cannot be negative. And what about the angle theta as you go around? That's the easiest thing. What will be the limits for theta? 0 to 2 pi. So it's no reason to worry about theta here. Okay, so the important one here is, of course, the z limits, which are not numbers because you're standing on imperfect surfaces. Okay. If z was both numbers, that will be flat surfaces. So these are inclined. That's why you have all these letters r in both the limits. So let me just summarize what I just did. So for this picture here, we have, using cylindrical coordinates, z is between r and 6 minus r square. That is the floor, that's the roof. R is between 0 and 2, and theta is between 0 and 2 pi. Once you have all that stuff, it's easy to find the volume, okay, because in cylindrical coordinates, the volume is the triple integral of 1 dz r dr d theta. Okay. Here you have to do z first because you got r in the limits. Okay. So don't just immediately go in and separate the things. Be a little bit careful here. So 1 dz r dr d theta. Z goes from r to 6 minus r square. That gives you the height of the solid. R goes from 0 to 2, theta from 0 to 2 pi. Understanding of the problem comes from the setup of this integral. Okay, after this, it's pretty much calculus 1. Okay. This is what I want to see mostly in problems where I say find the volume, find the mass or something. You know, this is what will show me whether you understand what's going on. Okay. Okay, let's quickly do this. Once again, before I separate it, just deal with this z variable carefully because there are r terms in both the limits. Okay. So the innermost integral is r to 6 minus r square 1 dz, which is 6 minus r square minus r. As always, that's just the roof minus floor height. Yeah, I mean, this is just the inner part, right, for z. So then comes, which r are we talking about?
Integral r
Just this part. Think I know what you're talking about. Just this part. You're talking about this R, right? That comes next. So they're doing it inside out. So just Z first. There's no need to keep R there. I mean, you could, but you don't have to. Yeah. Yeah. Because R is a constant with Z. So next, the middle integral. That's going to be the integral from 0 to 2. And that's where just have to be careful to include this R. Okay. So it's going to be 6 minus R square minus R times R dr. The outer integral is just 2 pi anyway. So, okay. So this is the integral of 6R minus R to the 3 minus R square dr. For all calculus 1 terms, this is 3R square minus R to the 4 over 4 minus R to the 3 over 3 from 0 to 2. Plug it in. So that's going to be 12 minus 4 is 8. 8 minus 8 thirds, which is 16 thirds. Dangerous to do these things without writing it down. Is that okay? 16 thirds. 8 minus 8 thirds, 24 over 3. Anyway, so the only part remaining now is the outer one. Okay. So this part you could have just separated and done it together, nothing wrong. So 0 to 2 pi of 16 over 3 d theta, and that's 16 over 3 times 2 pi, which is 32 pi over 3. I'm not surprised to find pi in there because it's got a circular cross section, and that is the volume of the solid. Okay. All right. That's problem 1. Any questions on this one? Let's do the second one, which I think we may have set up last week using XYZ, but we did not do it because it was not very easy to do using rectangular. Okay. So this is the one with the paraboloid and plane. Cutting it at the bottom. So later we'll be seeing spherical coordinates. Even then, I would still suggest that these problems, they are better used with cylindrical coordinates because there's nothing spherical about these surfaces. Okay. For spherical coordinates, I would suggest that you just use it if there is a sphere. So if there is no sphere, try to not use it. All right, example, sorry, worksheet 10, number 2. So this is the situation here. There's a paraboloid and there's a plane. And my suggestion would be to use cylindrical coordinates, though it does not say, and it won't say in the problem. We have to decide it. Can you set up the limits and write down the integral? Who's going to tell me the limits for Z? Maybe somebody online can either unmute or type it in. Can you say the lower and upper limits for Z here? It's
4 to 9 minus r squared.
good. So it's 4, that is the lower plane, to 9 minus r squared. That is after we decided that we will use cylindrical coordinates. Good. So that's the floor to the roof. Remember, we're using cylindrical coordinates, so don't bother trying to write y in terms of x or x in terms of y. That's exactly what we're trying to avoid here. What will be the limits for the r here? Somebody here can tell me. That's always 0, okay, unless there is another circle there. But what about the upper limit for r? Positive radical 5. Yeah? That's the radius of the disk that you created. So and that is the one that I wrongly wrote as 5 during the last lecture. Okay, so the square root of 5 is the radius. Unfortunately, it's not a clean number. That's okay. What about the angle theta? No surprise there. So root 2 pi. At some point, it kind of becomes a routine process. The volume is 1 dV. Once again, the Z has an R in the top limit. Okay, just be careful. 4 9 minus r square, r from 0 to root 5, and theta from 0 to 2 pi, 1 dz r dr d theta. So once you take care of the z limit, you could just do your integral like you did your polar coordinates in 3.3. Okay, so the height would be just z from 4 to 9 minus r square, which is 5 minus r square. There should be nothing surprising about the z result. Okay, that is telling you the height of the solid. So the total height there, since you're an elevated surface, is 5 minus r square. So this is the integral from 0 to 2 pi d theta. Now you can separate the integrals. Okay, and 0 to root 5. Just be careful about everything. This is 5 minus r square for the z part. And there is an r outside, that's r dr. Students, I know there's a lot of things going on. They forget to write this r. That's a mistake that you can avoid if you are careful. So this is 5r minus r to the 3. If you just distribute the r, and then the integral would be 2 pi times 5r square over 2 minus r to the 4 over 4 from 0 to root 5. Now this square and the fourth exponent, they are pretty good actually, because the square root works well with that. Okay. Square root of 5 square is 5. That's 2 pi times 5 times 25 over 2 minus 25 over 4. Square root of 5 multiplied 4 times. That's 50 over 4 here, 25, that's 25 over 4 times 2 pi. Which is 25 pi over 2. Okay. Just keep your calculator away from you, leave your answers in terms of pi. Okay. Questions? All right, so before we go into spherical coordinates, let's also try to do the ice cream cone problem from the last lecture. Okay. Today is actually a nice day to do it. So worksheet 10, number 3. We're going to do this problem again later using spherical coordinates. So you're trying to make it progressively easier with each. Okay. So this is the picture from the last lecture. Z equal to square root of 8 minus x square minus y square. I hope all of you now realize that x square minus y square term would be r square. Okay. So the hemisphere is now written as z equal to square root of 8 minus r square. And this one is, we're doing the same problem? Yeah. Z equal to r, which is the square root of x square plus y square. And this is what we kind of named as ice cream cone problem. Okay. And you're trying to find the volume. You can copy things from the last lecture if you want to, because we did this using XYZ there. I know I have most of the things written here, but still people, somebody online can tell me what the Z limits would be, please. Go ahead, unmute and say, or type it in the window.
From R to till the root of 8 minus r squared.
Good. Fourth roof. Okay. That square root will be a little bit annoying for us, but not too bad. Okay. So it goes from r to the square root of 8 minus r square. And we talked about the intersection of these two in the last lecture. Okay. It gives you the circular disk of radius 2. So the r limits would be from 0 to 2, theta from 0 to 2 pi. Looks much better than the integral we set up on Thursday with all the x and the y. Okay, that looked pretty hideous. Okay, this is at least just in terms of one letter, which hopefully can be taken care of. Sure. Which one? Is it? 2r square is 8. Oh, this should have been written right. 2r square is 8. R square is 4. So r is 2. 2r square, yep, right? Yep. So yeah, that should have been a 8. The guy sort of got excited there. All right, so the volume is what should we integrate again? What's that? 1. dz r dr. And please don't forget this r. Okay, in this problem it will create a whole lot of unnecessary problems if you forget this r. Other problems maybe it's just a computational thing. Here it's a nightmare. Okay, so this is r square root of 8 minus r square, 0 to 2, 0 to 2 pi. Let's do this carefully because it's a little bit of, I won't say difficult, but it's a little tricky to do this. Yeah. So again, the z part is the height of this ice cream cone. That is going to be the square root of 8 minus r square minus r. That minus r is outside the square root. So this is 0 to 2 pi d theta and 0 to 2 of this pair of terms, square root of 8 minus r square minus r dr. Did I forget something? The r. You forget that r, and as I said, that's going to create the complexity of the problem. Okay. Separate this into two terms. Okay. That's what you should do if you get a situation like this. This is just 2 pi. Integral from 0 to 2 square root of 8 minus r square times r dr minus the integral from 0 to 2 r dr. Sorry, r square dr. This integral is pretty straightforward. It's just r to the 3 over 3. Okay. So let me just write it here, 2 pi. I want your help with this one. How do you do this? This is easy. Okay. How do you do that one? U substitution. So u equal to what? Good. 8 minus r square. So du is negative 2r dr. Okay. Or r dr is negative 1/2 du. I think I told you this last week when we started this. U substitution just pops up here and there. Okay. So it's just going to write it without changing the limits. We will put the limits in later. So that's the integral of u to the power of half times negative 1/2 du. Yes, u is 8 minus r square, and then r dr is negative 1/2. The second term is easy. That's going to be minus r to the power of 3 over 3 between 0 to 2. This entire thing is being multiplied by 2 pi. So it's 2 pi times negative 1/2. The integral of u to the 1/2 is u to the 3/2 over 3/2, okay, which is 2/3 u to the power of 3/2 minus, this is just going to be 8/3 to the 3. You can cancel this 2 and 2, and you get 2 pi times negative 1/3. Now you should put u back in. U is 8 minus r square to the power of 3/2 between 0 to 2 minus 8/3. Now it might look like a negative answer. We are trying to find the volume. We know the volume shouldn't be negative. Okay, so that's taken care of by the fact that this is 8 minus r square. Okay, so when you plug in the limits, things will clear out. Don't worry. So this is 2 pi times negative 1/3.
Why is the second term third?
Because you had 2 to the power of 3. That is r to the 3 over 3. And you're going from 0 to 2, right? And you plug in the upper limit, which is 2. 2 to the 3 is 8.
Would you plug the lower limit of the first integral, the negative 1/3 times 8 minus r squared? Where do you plug the 0?
This one here. I haven't done it yet. I'm going to do it here. Yep. So I did the easy part first, separately. You could have kept that here, but then I just did it out of excitement. So this is negative 1/3 times. This is going to be 8 minus 2 square is 4. That's 4 to the power of 3/2 minus r equal to 0 will give you 8 to the power of 3/2. Okay, that's what you asked, right? Yeah. And then you have a minus 8/3. Not going to get a very clean looking answer, but at least we could convince ourselves that this is a positive number. Okay, 4 to the 3/2 is 4 to the 1/2 is 2, 2 to the power of 3 is 8, and 8 to the power of 3/2. Well, 8 to the power of 1/2 is 2 root 2 to the power of 3. And that's going to be 16 root 2. Just to make some sense of the answer and make sure that it's a positive number. Okay, so this is 2 pi times, we have a negative 8/3, then you have a positive 16 root 2 over 3, and then you have a minus 8/3. Now that's a positive number because you have 16 root 2 and this is just minus 16. Root 2 is more than 1. Okay, so this is 2 pi times 16 root 2 over 3 minus 16 over 3, which is 32 over 3 times root 2 minus 1. You don't have to beautify your answer. You could have probably left it here if you're running out of time or something. Okay, that's fine, but just to convince you that this is a positive number. Okay, so that is the ice cream cone problem using cylindrical coordinates. Okay. So a little bit intense, I would say, because of the U substitution, and you have to kind of keep track of terms. So I wouldn't call it super easy, but it's easier than the XY choice. Okay. And once you see spherical coordinates, then you know what to do. Okay. All right. Any questions? So that is the end of the cylindrical coordinates part of, but then now we're going to just see spherical coordinates, and then the question is which one is better for each problem. Okay. That is where you have to make some good choices. All right, I'm going to erase this. Any questions from anyone? Just do these problems once again. Okay. Get used to the setup and also the integration. All right. If you have never seen spherical coordinates in your life, please pay attention. It's a little difficult to get used to. Okay, once you understand the notations, things should be pretty easy. Just a very scary appearance, but it's just the look. Okay. Spherical coordinates, as the name says, it's best suited for anything that is spherical in shape. Okay. So if you take a cylinder and try to use spherical coordinates, it probably is not a good idea. It has to have some kind of a spherical geometric thing attached to it. The origin of spherical coordinates, it's, as you can guess, it is for navigational purposes. Okay. Yes, 99% of people on this planet believe that Earth is spherical in shape. Okay, so that is the whole purpose of defining spherical coordinates. We kind of ignore that other 1% who think it's a flat planet. That's not our problem. All right, so we think about a sphere which is centered at the origin, just for convenience. Let's define rho to be the radius of the sphere. That's a Greek letter rho. We don't use r, and I'll tell you why. Okay. First of all, we already use it in polar coordinates. We don't want to use it here. Okay. So this is rho. So since it's radius, it has to be a positive number. So 0 less than or equal to rho less than infinity. As you can imagine, that is the distance from the center of the sphere to the farthest point out here. There is also the angle theta that kind of goes around like this. Okay. So theta is the same as your polar coordinates. So theta is called the azimuthal angle. Unfortunately, if you are a physics major, okay, they use a different letter for this. So if you're taking this and a physics course at the same time, you'll go crazy. So for us, we'll keep theta to be uniformly the same kind of angle that we have been seeing. Okay, it's on the XY plane that just sweeps an angle of 2 pi radians. Now the third thing is the mysterious thing. Okay, that's where you have to pay attention. So I'm pretty sure that all of us are familiar with these terms. This is the North Pole. This is the South Pole. And for our navigation understanding, that is the equator. Okay. So there is a third angle that kind of sweeps the planet from the North Pole to the South Pole. And that's the only new thing that you have to get used to. Okay. So phi is the polar angle that starts from the North Pole. The North Pole is actually in the positive z-axis. Okay. The reason why this is weird is because this is being traveled clockwise. So it starts from the North Pole, goes clockwise to the South Pole, and stops there. You might think, why not you go back to the North Pole? Okay. So that's where you have to be a bit careful to understand what's going on. So I'll redraw this sphere once more. Okay, so this is where you start, phi equal to 0. That's the North Pole. Okay. So you reach some point here on the surface of Earth. Okay, maybe it's a Tropic of Cancer, I don't know, or Arctic Circle. Okay. At this point, if you fix the value of phi, you could just go around the planet once and come back there. Okay. Almost like a ring that you can form around the planet. Similarly here, you could form another ring, go around, come back. Okay. Equator. By the time you reach the equator, it is half of the planet, so it is pi over 2. Again, the Tropic of Capricorn is somewhere here, and then the South Pole is here. Okay, so by the time you reach phi equal to pi radians, you have covered the whole planet, because at each value of phi, you can just go back once. Okay. So that is why the limits for phi don't go from 0 to 2 pi, because you're going from North Pole to South Pole and you stop there. Okay, because you have, for each value of phi, you're able to do this circular journey once and come back to where you start. So phi is called the polar angle. For obvious reasons, it goes from pole to pole. Okay. And the limits are 0 less than or equal to phi less than or equal to pi. This is clockwise. Clockwise is positive, this is anti-clockwise. And if you ask a navigational person, they would probably tell you that their phi goes from negative pi over 2 to pi over 2. That's because they measure things from the equator. Okay. For our purposes, it's easy to keep things positive. That's why we start from the North Pole. So North Pole is 0 and South Pole is pi. Okay. So if you are a maritime person who does things the old-fashioned way, for navigational purposes, you start from the equator, so negative 90 degrees is less than, they don't use radians, less than or equal to phi, less than or equal to 90 degrees. That gives you the polar angle with respect to the equator to the North Pole and the South Pole. And their theta actually starts from the center of the vertical axis. So it's negative 180 degrees less than or equal to theta less than or equal to 180 degrees. We just shift everything to 0 because it's easier for us to calculate. Okay. Instead of doing this, we just do 0 to 2 pi starting from the positive x-axis. I don't know if all of you are familiar with this. Just like the equator, there is an imaginary central thing here. Do you know what that is? The prime meridian. Okay, so that is where the navigational people kind of measure their theta. Okay. The prime meridian passes through a very important city in England, passes through Greenwich. And that's why all the time zones are defined with respect to the prime meridian. Okay. All right, so that's some geographical details. Yep.
Can you split regions when you're like trying to find the bottom? Okay, sorry, if it's solid. Can you split them and use different coordinate systems?
That's a bad idea in general. Yeah, you just stick to one thing for a single problem. I mean, I haven't really come across any problem where it's a good idea to do cylindrical coordinates and spherical coordinates the same problem. That could be very confusing because you are dealing with the same radius in two different ways. It's a dangerous thing to do. I won't say it's bad, but dangerous thing to do. Totally not recommend. Nothing is wrong. You could just do it in terms of x, y, z, right? And that's also correct, right? It's all about convenience. Okay, so apart from that, okay, please pay attention to copy this correctly. Theta goes from 0 to 2 pi. Phi, that looks like theta, it's phi. Okay, goes from 0 to pi. That is the polar angle, goes from North Pole to South Pole. All right, now we need to understand how these things kind of evolve from polar coordinates. Okay. So this is your xy plane, r, and this angle is theta. X equal to r cosine theta, y equal to r sine theta. I don't want this to make it some kind of a memorizing game. Okay, so let's start with things that we know and then build into things that we don't know. Okay. And this is what we are trying to do. This is the three-dimensional space with a new radius rho, which is defining your point P. Okay. So one is rho, the other one is P. Okay. And your angle phi is defined from here. The phi starts from the North Pole clockwise. Your radius r is still on the xy plane. Okay. And it's done counterclockwise from the positive x-axis towards the y-axis. So the angle theta here would be this way. So just looking here on the xy plane, theta starts from the positive x-axis to y-axis. Okay. So we need to find out the relationship between r and rho. They are not the same. Okay. R is kind of on the flat plane, rho is somewhere in the three-dimensional space. Okay. So the first question is, what is the relationship between r and rho? And the second thing is, how do we express z in terms of rho? So let's just form so this is the line that is going from the point O to some point here. Let's call this P1. Okay. And let's draw a line parallel to P1 here. So these lines are parallel. Which means that this is now a 90-degree triangle or a right angle triangle. Yep. P is sitting in the space, so it's not really in any plane. Okay. P is sitting like here. So unless you are projecting it onto any plane, it's not on any particular plane. It's in space. But I cannot draw that here. It will look like it's sitting on a plane because we are drawing on two-dimensional surfaces. Right? But P is literally hanging like that microphone there. Yeah, that's what it is. So let's define this height as Z because that is along the positive Z axis. Okay. Now, if you look at this picture carefully, and if you pardon the imperfections of drawing, this length is same as this length up here. That's also R. This OP1 is the same as this parallel line up there. So if you take the sine of the angle phi, its opposite side over hypotenuse, which is R over phi, R over rho, a lot of Greek letters, opposite side hypotenuse. So R is rho sine phi. So you're traveling from polar cylindrical coordinates to the spherical coordinates now. Okay. R equal to rho sine phi. And similarly, if you take the cosine of phi, you get adjacent side over hypotenuse, which is Z over rho. So Z equal to rho cosine phi. Okay, so now we can convert everything in terms of x, y, z into rho theta phi. Okay, so x would be r cosine theta, r is rho sine phi, so it's rho sine phi cosine theta. Y is r sine theta, which is going to be rho sine phi sine theta. Okay, so just plugging in. Now we have completely transformed ourselves from rectangular to spherical coordinates. Okay. And z is rho cosine phi. So it looks complicated now because we have to pay some price for making your life easy. Okay, so it was x, y, z. Now it has become complicated. Okay, so this is the corresponding things for the spherical coordinates in R3. And if you square and add this, x squared plus y squared plus z squared, it says Pythagoras theorem, these have some sine square plus cosine square terms. Okay, that will become equal to rho square, not rho. So x square plus y square is r square. And if you add the z square term, okay, this is r square, and then r is rho square sine square phi. This is rho square cosine square phi. Add them together, get rho square. Okay. This is the hint that spherical coordinates is a good choice. If you have a block of term that looks like x square plus y square plus z square, or a sphere or a part of a sphere, okay, that's a hint that using spherical coordinates is a good choice. So we started from things we know. We developed the conversion for rectangular to spherical coordinates. There's only one thing remaining now. What is that? What is a dV? Okay, that is a part which will take some. It's a little rough when you look at it. Okay, but it serves a purpose. So let's. To forgive my horrible picture drawing skills, but it has to be a three-dimensional spherical volume element like this. Okay. Brutal, right? Okay, so you're taking a sphere, or maybe take an apple and just slice it, okay, radially, so that you get a small chunk of it. So what we're trying to do is this. This is your rho, and taking a small part here. It's three-dimensional because there is a thickness and there is a radial and angular component. Okay. So this radius is d rho, that is a small increment. This is phi, and this is d phi. As usual, we have an increment which is both in terms of the radius and in terms of the angle. Okay. So the length of this arc would be rho d phi. That's because it's the radius times the angle. That tells you the length of the arc for this particular thing. That is what is shown here. This side is just d rho. This is now again in space. So this one? Oh, that's because I didn't want to make it because of my artistic skills. This is actually in. This is where things go ugly. This is like this. Okay. Everything is in space. There's nothing in 2D here. Okay. We are no longer in 2D. We are in R3, except that because of my horrible drawing skills, things have to be limited in terms of.
So it's the thickness of that thing.
This is r d theta. This is same as what you had. So what you're doing here is, this is your XY plane. Okay. This part is r d theta, and that is forming the height here. So there are three components here: the rho d phi that comes because of this arc length, the r d theta that comes from the polar coordinates, and the increment in radius, which is d rho. But r is rho sine phi. Okay, because of this thing here. R equal to rho sine phi because of what I wrote up there. Okay. So the three length components that make up this curved volume are d rho times, so d rho is this length, okay, times rho d phi, which is this arc length, times this height, which is actually the projected length of this arc length up there. Okay, you're just projecting it into 3D and forming this height here. And that's going to be rho sine phi d theta. So you still have a height and a length and a width but these are all kind of curved because it's a spherical element. Okay. So the dV is going to be rho square sine phi d rho d phi d theta. So it's the most complicated of the dV things. In XYZ, it was pretty easy. It's just dx dy dz. In polar coordinates, got a little bit difficult because of the r dr d theta thing. Okay, here it's completely kind of out of control because you're converting from rectangular to polar to spherical. Okay, so it has to go through all those conversions and to give you this particular thing. There is a linear algebra way of deriving this, which is beyond the scope of this course, and that's probably the better way to do this. That way I don't have to draw pictures, but it's beyond the scope of this course. All right, so let's too much to summarize here. Okay, so the first things you should keep in mind are the limits of the three variables. Radius is always positive. Your theta, nothing has changed. Phi is the new thing. Okay, goes from pole to pole along the z-axis from the positive to the negative z-axis. Okay, it should stop there. Do not go back on phi. Okay, just one sweep. The conversions from x, y, z to rho theta phi are up there. And again, the relationship is that x square plus y square plus z square equal to rho square. Actually, we wrote this in the first or second lectures. Remember the equation of a sphere with center at the origin. When we did the distance formula, I think I wrote it quickly. Okay. And most importantly, the dV component. You don't have to memorize this, okay? And you don't have to derive it. The key thing is to copy it correctly. Don't miss the square here. Don't miss the sine of phi, not sine of theta. Okay, d rho d phi d theta. So I'm not writing it again because it's again going to be a lot more writing. So hopefully things are clearly written out there for you to see and copy correctly. Any questions? Yeah. If it is not, when you say not a perfect sphere, as in ellipse, probably not. For there, you have to come up with an elliptical coordinate system. It will only work for a spherical coordinate system and some geometric things that you can kind of nicely manipulate with it. Okay. Yeah. But try to not use it for a cylinder or a paraboloid. They're, not a good combination. Yeah.
So the reason that's why it was allowed to between spherical cylindrical coordinates was for the ice cream. So it's like sphere on top.
Oh, there you would see that the spherical coordinates fits perfectly. I'll show you. Okay. Ice cream cone is one of the best places where you could use spherical coordinates. You may not believe it, but you will see that. All right, first let's check whether this is true. Okay. Do you know the volume of a sphere of radius r from middle school or high school? All right, so it used to be 4/3 pi r cube, but then you just believed it, right? How do you know it's right? Because your high school teachers told you so. Let's see. This might just wow you with spherical coordinates. You'll just get the answer and chop, chop, chop. So find the volume of a sphere. It's centered at the origin, just for convenience reasons. Okay. Sphere of radius r. Keep all these things right next to you when you do spherical coordinates. You need all that information because I don't want to keep on rewriting all these things. Okay. So find the volume of a sphere of radius r centered at the origin. And I heard some of you say the answer as 4/3 pi r cube. But then you were just forced to believe that is true. Yeah. No reason why there's a 4/3 for a sphere. I mean, why? All right, so let's do it using spherical coordinates. Okay. Well, it's a sphere, use spherical coordinates. Don't forget the volume is integral of 1 dV. Triple integral. And dV is all that stuff I wrote there. Okay, so it's rho square sine phi d rho d phi d theta. Just make sure that you put the appropriate limits. It's a full sphere. Okay, the radius goes from 0 to r. The second variable I put here is phi, so let's write that one. Phi goes from 0 to pi. Okay, don't forget, pi is the polar angle. And theta sweeps through the entire circumference, so it's 0 to 2 pi. Look at that, all of them are numbers. We could just separate them. Okay. So it's 0 to 2 pi d theta, 0 to pi sine of phi d phi, and 0 to r rho square d rho. I told you math is easy. Go 3 integrals in calculus 1, just multiply it out. Okay. That is 2 pi. What is integral of sine? This is the only problem I have. Negative cosine. Yeah. Otherwise, you'll end up with a negative volume and you'll be like, oh, something is not right. It's negative cosine from 0 to pi. And this is going to be rho to the power of 3 over 3. 0 to r. You can slowly see things are evolving here. Okay. This is a multiplication. So this is 2 pi. That's going to be negative cosine pi minus cosine 0. Okay. Times r to the power of 3 over 3. Okay, so you got bits and pieces. You got a pi, you got an r to the power of 3 over 3, you got a 2. The question is, what is this term? Well, cosine of pi is -1. Okay. So this is negative of -1, that's positive 1. And this should be a plus because you have a negative of negative. Sorry. Okay. This negative So it's minus the lower limit. That's going to be minus cosine, minus negative cosine 0. That's plus cosine 0, which is also plus 1. Or you could factor the negative sign outside if that is too confusing for you. So what is the answer? 4/3 pi r cubed. Actually, less than a minute if you use the right coordinate system.
Sorry, out of curiosity, were these coordinate systems used to prove these like areas and volumes, or were they like
These were given mathematical meanings to prove these areas and volumes, yes. And then navigational people found that, oh, this is actually making sense with their maps and projections and everything.
I assume that this came afterwards.
Yes, this came much later because mathematics evolved much late in the 18th and 19th centuries. People started traveling even before that. So, but once math started giving meanings to these things, people started using it. Yeah, I don't think people knew about the calculus till 18th century. And if you think about it, the volume of a cone, okay, is 1/3 pi r to the power of square h, where h is the height. The idea is that if you take a liquid or a conical container full of water and try to fill a sphere, okay, it will take exactly 4 of these to fill this. That is why there is an intuitive number of 4 in there. Okay. 4 of these to fill up this. It's assuming that the height has the same radius. Okay. So that is the intuitive idea behind why there is a 4 multiplying the volume of a cone, if you ever think about it. I think there are some YouTube videos trying to kind of animate this process. It's easy, it's nice to watch those things. I cannot really draw that here because I have limitations. All right. Let me give you a slightly different problem. Okay. Can you find the volume of the first 1/8 of a sphere without cheating? Okay. Now, if you take an apple and then cut it in half, and then further cut it into just 1/4 of it. So that's 1/8 now. Okay. So find the volume of sphere, or volume of a part of a sphere the first octant, which by its name should tell you it's the volume of 1/8 of a full sphere. Now, if you want to cheat, the answer is this: 1/8 times 4/3 pi r cubed. But my question is, can you set up an integral and try to do this? This is 4/24, which is pi r to the 3/6. That's what you should expect. But if you were to set up the triple integral and then keep the radius at r, okay. So what's the volume of 1/8 of an apple? So I'm going to write the limits here. Okay, so yep. Oh, you mean 1/8 of the integral earlier? Yeah, that's still cheating. Yeah, that's kind of semi-cheating, less cheating, yes. The whole point is to see if you understand the limits. I've written one of them first. Okay, the radius goes from 0 to r. So the question is, what are the limits for theta and phi? Remember that the first octant is first quadrant plus the first quadrant and above the XY plane. Okay, that is what it means. For the rest of the semester, please keep that in mind. Okay, the first octant means everything is positive. On the XY plane, it's the first quadrant, that part, and it's above the XY plane. Nothing is negative. All right, so from the fact that it's in the first quadrant, theta will go from 0 to pi over 2. What about phi? It's also 0 to pi over 2 because when you say above the XY plane, this is stopping at the equator. Okay. This is your XY Z axis. This is the equator. Okay. This is what the first octant would stop at. Yeah. So this is starting from phi equal to 0, North Pole, phi equal to pi over 2, equator. All right, so now we can find the integrals, which are pretty easy. 0 to pi over 2 with theta, 0 to pi over 2 sine of phi d phi, and 0 to r rho square d rho. And the first term is pi over 2. Times integral of sine, again, this is negative cosine. Okay. From 0 to pi over 2 times rho to the power of 3 over 3, which is r to the 3 over 3. I know this negative is a little bit of a nuisance. Okay, you can either pull it out so that you don't make mistakes with this. This part would be cosine of pi over 2 minus cosine 0. Okay. Cosine pi over 2 is 0. This is 1. So you have negative of negative 1. So this entire thing is 1. So the answer is, math works, right? If it gave you a different answer, then something is wrong. Okay. So no matter which eighth of the sphere you take, the total volume would be 1/8 of the total volume. All right, now let's go back to our worksheet and attack. So what we'll do is we'll just set up those problems in spherical coordinates, and then I'll write the solutions for that and leave it online so that you could, so that way we can say, because none of these integrals are difficult to do. Okay, so let's just focus on setting up. Let's start with number 4, which is number 3. One last time, here is the ice cream cone. this point, you should be able to look at the hemisphere and just move the terms to get the radius of that sphere or hemisphere. Okay. So this is rho square. So rho is the square root of 8. So the limits for rho are pretty straightforward. I know it's not a very nice looking number, and which probably might explain the square root of 2 in your answer earlier. Remember, there is no z in spherical coordinates. Okay. What about theta? That should be easy. So 2 pi. Okay. The only place where theta is going to change is if it is in the first octet. Okay. Otherwise, theta just sweeps through the entire circular region, and that gives you from 0 to 2 pi. It's all about phi now. Don't forget, phi starts from the North Pole. Okay. So this is your phi. Okay, so as usual, it starts from phi equal to 0 to phi equal to something. This is probably the only unbelievable part of spherical coordinates. Okay, when you write this in spherical coordinates, you get rho cosine phi equal to rho sine phi. The z is rho cosine phi. I think I erased it, but in spherical coordinates, this is rho cosine phi. This part is r, okay, and r is rho sine phi. You can cancel the rho on both sides, and you get tangent of phi equal to 1. What value of phi in the first quadrant gives you tangent of phi equal to 1?
Back up like 15 seconds.
Sure. So in spherical coordinates, we did this z equal to rho cosine phi, and then r equal to rho sine phi. And since x square plus y square is r square, the square root of that is square root of that is r. Okay. So since these two are equal on the cone, you have rho cosine phi equal to rho sine phi. And if you divide both sides by cosine of phi, you get tangent of phi equal to 1. That gives you a number for phi. What is that? Pi over 4, okay, 45 degrees. So the cone, which looked like a pretty difficult thing to do in spherical coordinates, is actually a number in spherical coordinates. Okay. Starts from the North Pole, stops at this line, and it goes from 0 to pi over 4. All right, so now we have the volume equal to the triple integral of 1 dv, which is rho square sine phi. You don't have to memorize this, just look into your notes or formula sheet, whatever you have. Make sure that it is written correctly. It's rho square sine phi, not theta. D phi d theta. Okay. All of these are numbers now. It doesn't matter which one you do first or last. Okay. So this is 0 to square root of 8, 0 to pi over 4, and 0 to 2 pi. The numbers will be a little bit unpleasant because of the square root of 8, but it's not hard. There is no u substitution or anything. Okay. So that is the setup. Again, I'll post the solutions for this tomorrow after we finish the worksheet. Okay. You can just separate it and do it one by one. So it's not a All right, so we will do the remaining 3 examples when we start our lecture tomorrow. Okay, so it's 5, 6, and 7. Again, during the lecture, I'll set up, and you should try to do this yourself as a good practice for the test, and then we will start the last section tomorrow. All right, I have office hours at noon today, tomorrow, and on Wednesday at 12:10, actually, not noon. Okay, so feel free to stop by if you have any questions about any of these. And, yeah, we'll do more examples tomorrow. All right, thank you. Yeah, sure. Go ahead. You can ask the question about the test. Just unmute or you can type.
Professor, for questions that where we have to reverse the order, will we always be told to reverse the order, or sometimes we have to
Yes,
think
yeah.
about it?
For that problem, I'll tell you to reverse the order. Yes.
Thank you.
Yeah. Though it should be obvious that from the way the problem is sitting, but then maybe it's unfair to expect you to know that. So I'll just mention it there. Okay.
Thank you, Professor.
Yeah. Any other questions? All right. So tomorrow will be another busy day for us.